In June of 2026, Microsoft stood on a stage and claimed it had solved a problem that has haunted quantum physics for 3 decades. Then, within days, physicists who have spent their entire careers in this field started laughing. Not because Microsoft was lying exactly, but because this is not the first time they have made this precise claim. Back in 2021, they published what looked like the same breakthrough in the journal Nature. It got retracted. Outside, experts picked apart the data and found that what Microsoft was calling evidence of a new kind of quantum particle could just as easily be explained by ordinary material defects. So when the company came back 5 years later with an upgraded chip and another set of extraordinary numbers, the reaction from a lot of serious researchers was not excitement. It was a raised eyebrow and a very long pause. So what is actually different this time? And more importantly, why are Microsoft, Google, Caltech, and a 14-person startup working out of a borrowed office near Caltech's campus all racing toward the same finish line at the same moment, using artificial intelligence to get there faster than anyone predicted just 2 years ago? That is the story I want to walk you through today, carefully, honestly, without the exaggeration that has been clogging up your feed all month. Let's start with what Microsoft actually announced, because the details matter here more than the headline. On June 2nd, 2026, at Microsoft's Build conference, the company unveiled a new chip called Majorana 2. It is the successor to Majorana 1, which was introduced back in February of 2025. The pitch is built around a concept called topological quantum computing, an approach that tries to store information in a way that is naturally resistant to the errors that plague every other quantum architecture on Earth. To understand why that matters, you need to understand the actual obstacle that has been blocking quantum computing from becoming useful for the last 30 years. It is not processing power. It is not funding. It is a phenomenon called decoherence. Qubits, the quantum version of the ones and zeros inside a normal computer, are absurdly fragile. A stray vibration, a tiny shift in temperature, even a passing cosmic ray can knock a qubit out of its quantum state and corrupt whatever calculation it was in the middle of. Every quantum computer ever built has had to fight this problem, and for most of them, a qubit survives in a usable state for somewhere between microseconds and milliseconds before it degrades. That is the wall. Microsoft's claim is that Majorana 2 punches straight through that wall. According to the company, the new chip's qubits maintain their quantum state for a mean lifetime of 20 seconds, with some individual instances holding stable for a full 60 seconds. Compare that to microseconds, and you start to see why Microsoft is calling this a 1,000-fold improvement in reliability. The company's own analogy is a phone battery that used to die within a day, suddenly lasting 3 years on a single charge. The key materials change, according to Microsoft, involved swapping aluminum for lead as the superconducting material inside the chip. Lead apparently offers better natural shielding against the kind of background disturbances that cause qubits to collapse, though working with it introduced engineering headaches that reportedly took years to solve. And here is the detail that connects this story to everything else we're about to cover. Microsoft says it did not get here through traditional trial and error alone. It used an agentic AI system called Microsoft Discovery, a platform that deploys teams of AI agents to autonomously explore materials, science problems, run simulations, and propose configurations that a human research team would take far longer to stumble onto. Microsoft Discovery became generally available to the public on the exact same day Majorana 2 was announced, which tells you the company sees these two things as one unified story. Artificial intelligence did not just benefit from this chip. Artificial intelligence helped build it. And the company is now betting that it can build a scalable quantum computer by 2029, a timeline it cut in half from its original 2033 target, specifically because of what this chip demonstrated was possible. Now here is where the skepticism comes in, and I think you deserve the full picture rather than just the highlight reel. This work has not gone through the traditional peer review process. What Microsoft has released is closer to a technical manuscript and a public demonstration than a fully vetted scientific paper. Independent physicists outside the company have pointed out that the headline numbers appear to come from a small number of standout instances on a single device, not from a broad, reproducible data set. One researcher who specializes in this exact field put it bluntly, saying that you can observe something remarkable on one device and never see it again because it turns out to be a random artifact rather than a genuine breakthrough. Another physicist who has followed Microsoft's topological quantum program for years described the general reaction among specialists as somewhere between a chuckle and a raised eyebrow whenever Microsoft makes one of these announcements. That reaction did not come from nowhere. It comes directly from the 2021 episode, when Microsoft published a paper in Nature claiming they had detected Majorana particles, the theoretical building block their entire approach depends on. That paper was retracted after outside scientists demonstrated that the supposed signature of these exotic particles could be produced by mundane material defects instead. So when Microsoft returns in 2026 with round 2, the scientific community is not rejecting the claim outright. They are simply insisting on the thing that separates real breakthroughs from hopeful announcements, which is independent verification, replication by outside labs, and full technical transparency that lets other scientists actually test what is being claimed. Until that happens, Majorana 2 should be understood as a genuinely interesting engineering claim from a company with a track record of overselling this specific technology, not a settled science. Contrast that with what Google has done, because the difference is instructive. Back in October of 2025, Google's Quantum AI division ran an algorithm called Quantum Echoes on their Willow processor, a chip built using a completely different architecture than Microsoft's, based on superconducting qubits rather than topological ones. The formal name for the algorithm is the out-of-time order correlator, a tool that measures how disturbances spread and interfere with themselves across a quantum system, something researchers sometimes describe as a kind of quantum butterfly effect. When Google ran this calculation using 65 of Willow's 105 qubits, it completed the task roughly 13,000 times faster than the best classical algorithm running on Frontier, one of the most powerful supercomputers currently in operation. To put that in perspective, a calculation that would take a world-class supercomputer years to finish took Willow a matter of hours. And critically, this result was not just announced in a press release. It was published in Nature, meaning it went through independent peer review, and unlike many previous quantum supremacy claims, the result is actually verifiable. Researchers can check the output either by rerunning it on a separate quantum computer or by comparing it against real physical measurements of natural systems that behave the same way. Google's chief scientist for quantum hardware, a Nobel laureate named Michel Devoret, has pointed to this verifiability as the real headline, arguing that it marks the difference between a party trick and a genuine scientific tool. The practical applications researchers are excited about involve modeling molecular structures, chemical bonds, and material properties with a level of precision that classical simulation simply cannot reach, which could eventually feed into drug design, battery chemistry, and catalyst development. It's worth taking a moment to explain why this particular category of calculation matters beyond the raw speed number, because the 13,000 times figure on its own can sound like an abstract flex rather than something with real consequences. The reason researchers care about simulating molecular behavior with this level of precision comes down to a basic limitation of classical computers. The interactions between atoms, the way electrons arrange themselves around a molecule, the way a potential drug compound might bind to a protein in the human body, all of that behavior is governed by quantum mechanics at its root. Classical computers can only approximate that behavior, essentially building a simplified model and hoping it's close enough to reality. Quantum computers, in theory, do not need to approximate anything, because they are themselves quantum systems, obeying the same physical rules as the molecules being simulated. That is the entire premise behind why fields like drug discovery, materials science, and battery chemistry are watching this space so closely. It is not that quantum computers will simply run existing simulations faster. It is that they may eventually allow scientists to run simulations that are accurate enough to actually trust, rather than accurate enough to be a reasonable guess. That distinction is the difference between a drug candidate that looks promising on a screen and one that survives contact with an actual clinical trial. I want to pause here and flag something important about timing, because it matters for how you should interpret any video claiming this is breaking news. The Willow result is genuinely remarkable, but it happened in October of 2025, roughly 8 months before most of the viral content currently circulating about it. A lot of what you're seeing online right now is repackaging an 8-month-old peer-reviewed result and presenting it as if it happened last week, often stitched together with newer announcements to create a false sense of an accelerating all-at-once moment. That does not make the underlying science any less real. It just means you should be suspicious of any framing that tells you this specific result is brand new. The actual new development in this space, the one that genuinely did happen recently, involves a much smaller and less famous player, and it might be the most consequential thread in this entire story. In late March of 2026, a 14-person startup called Oratomic launched out of Pasadena, California, built around a collaboration with Caltech. The founding team includes researchers who came from Caltech, Harvard, Berkeley, Amazon, and Google, including physicists like Manuel Endres, John Preskill, and a researcher named Xinyuan Huang, who goes by Robert, and who had previously worked inside Google's own quantum AI division before taking a leave from his Caltech faculty position to help lead the new company. The startup published a paper alongside its launch, posted to the arXiv preprint server, arguing something that upended a long-held assumption in the field. For years, the general estimate for how many physical qubits you would need to build a genuinely useful, fault-tolerant quantum computer, capable of running serious algorithms hovered around 1 million. That number came from the overhead required for quantum error correction, since protecting a single reliable logical qubit from noise typically requires bundling together roughly 1,000 physical qubits to check each other for mistakes. Oratomic's paper, developed in close collaboration with Caltech physicists, including Endres and Preskill, proposed a new error correction architecture using neutral atom qubits that can be dynamically rearranged. And the headline result was that a genuinely useful quantum computer might require as few as 10,000 to 20,000 qubits instead of 1 million. That is a reduction of roughly 100 times. Here is why that number should get your attention, even if you don't care about quantum computing in the abstract. One of the things a sufficiently powerful quantum computer would be capable of is running an algorithm developed back in 1994 by the mathematician Peter Shor, an algorithm specifically designed to factor extremely large numbers with a speed that classical computers cannot match. That capability is not just academic. Nearly every encrypted system currently protecting the internet, your banking information, your medical records, government communications, relies on the fact that factoring these large numbers is essentially impossible for classical hardware within any reasonable time frame. If a quantum computer can run Shor's algorithm at scale, that entire foundation collapses. For years, the working assumption was that this threat was decades away, comfortably beyond the horizon, because nobody could build a quantum computer with 1 million stable qubits. Oratomic's paper suggests that threshold might be 10 to 100 times closer than anyone thought. To understand why cutting that number from 1 million qubits down to 10 or 20,000 is such a big deal, it helps to understand what quantum error correction is actually doing under the hood. Individual physical qubits are unreliable on their own, prone to collapsing out of their quantum state from the smallest disturbance. So researchers bundle groups of physical qubits together into what's called a logical qubit, where the group constantly checks itself for errors and corrects them faster than they can accumulate into a real problem. The trade-off has always been overhead. Protecting one reliable logical qubit historically required roughly 1,000 physical qubits working together, which is why a computer needing 1,000 logical qubits to run something like Shor's algorithm ballooned into an estimate of 1 million physical qubits total. Oratomic's proposed architecture, built around neutral atom qubits that can be physically moved and rearranged in real time using laser tweezers, claims to dramatically shrink that ratio. Fewer physical qubits needed per logical qubit means a smaller, more achievable machine, and a smaller, more achievable machine means the timeline for building one collapses along with it. That is the mechanism behind why a single theoretical paper caused this much movement among cybersecurity teams within days of its release. And this is where artificial intelligence enters the story again, more directly this time. One of the paper's authors, Oratomic's CEO Dolev Blovstein, told journalists afterward that there was no ambiguity about it, that artificial intelligence had directly accelerated the development of their error correction algorithm. The published paper itself does not spell out exactly how AI was used in deriving the core results, a choice the team reportedly made deliberately, given the sensitivity of the topic. But Blovstein confirmed the team plans to publish a follow-up paper detailing that process specifically. What's striking is how quickly the security world reacted once this became public. A cybersecurity researcher at Cloudflare, a company that secures a significant portion of global internet traffic, described the reaction inside his field as something close to a genuine shock, and said teams were scrambling to accelerate their preparations. Within days, Cloudflare publicly moved up its own deadline for transitioning to quantum-resistant encryption to 2029. Google did something similar, announcing its own internal timeline to secure its systems against quantum attacks by 2029 as well, 6 years earlier than the original 2035 deadline set by the National Institute of Standards and Technology. This is not hype dressed up as urgency. This is some of the most conservative, security-focused organizations on the planet independently deciding to move up their timelines within the same week that this research became public. There is a strategy that security researchers refer to as harvest now, decrypt later, and it is worth explaining clearly because it changes how you should think about all of this. Intelligence agencies and other well-resourced actors do not need a working quantum computer today to benefit from one in the future. They can simply intercept and store encrypted data now, banking on the assumption that at some point in the coming years, quantum hardware will catch up to the mathematics and allow them to decrypt everything they've archived. This is not speculation. It is an acknowledged strategy that multiple governments have openly discussed as a concern. The Oratomic and Caltech findings do not mean encryption is broken today. Nobody has built a 10,000 qubit fault-tolerant quantum computer, and the engineering challenges between a theoretical paper and a working machine remain substantial. But the estimated distance between where we are and where that threat becomes real just got dramatically shorter, and the transition to post-quantum encryption standards that the National Institute of Standards and Technology finalized back in 2024 suddenly looks a lot more urgent than it did a year ago. Now let's talk about the money, because it tells you how seriously institutional investors are taking all of this. In early June of 2026, a company called Quantinuum went public on the NASDAQ under the ticker symbol QNT. Quantinuum was formed back in 2021 through a merger between Honeywell's quantum computing division and a British company called Cambridge Quantum, and it describes itself as a full-stack quantum computing company, meaning it builds both the hardware and the software layered on top of it. The IPO itself was upsized twice as investor demand grew, eventually pricing at $60 a share for 28 million shares, raising $1.68 billion in gross proceeds and giving the company an initial valuation of roughly $17.6 billion. That is a serious number for a quantum computing company, and it made headlines as one of the largest public offerings the sector has ever seen. But if you actually read the company's financial filings, the picture gets more complicated. Quantinuum reported a net loss of $192.6 million for 2025, followed by another $136 million loss in just the first quarter of 2026. Its revenue for that same first quarter actually dropped 73% compared to the year before, falling from about $19 million down to just over $5 million. Bookings, which track the total value of new customer contracts, came in at just $1.3 million for the quarter, down from $1.9 million a year earlier. In other words, investors piled $17 billion of valuation onto a company that is currently losing more money than it makes, and whose near-term commercial traction is, at best, uneven. That does not necessarily mean the bet is wrong. Honeywell retains a majority ownership stake and continues functioning as a strategic partner. And the technology itself, based on trapped ion qubits rather than superconducting or topological ones, has posted genuinely impressive fidelity numbers in its own right. But it does mean the Quantinuum IPO should be read as a bet on where quantum computing is heading over the next 5 to 10 years, not as proof that the technology is already commercially mature. Some analysts covering the stock have been blunt about this, describing the valuation as more than 500 times the company's current sales and characterizing it as a speculative wager, riding on broader quantum hype rather than near-term fundamentals. So where does this leave us? You have Microsoft making an extraordinary but unverified claim backed by a company with a documented history of overselling this exact technology. You have Google with a genuinely peer-reviewed, independently verifiable result that is real, but roughly 8 months old by the time most people are hearing about it. You have a small, serious research collaboration out of Caltech that just quietly rewrote the assumptions about how close we are to quantum computers, capable of breaking modern encryption, using artificial intelligence to get there and triggering immediate defensive moves from major internet infrastructure companies. And you have public markets pouring billions of dollars into companies whose underlying revenue does not yet come close to justifying those numbers, on the belief that the technology curve is about to bend sharply upward. None of these threads exist in isolation anymore. Artificial intelligence is now showing up inside the actual research process at nearly every one of these organizations, not as a chatbot answering questions on the side, but as an active participant in discovering new materials, new error correction architectures, and new algorithmic approaches that human researchers were not finding on their own. Microsoft used agentic AI to help design the material stack inside Majorana 2. Or Atomic used AI to help develop an error correction breakthrough that has already reshuffled global cybersecurity timelines. This is the feedback loop that is actually worth paying attention to. More than any single announcement, better AI systems help researchers explore quantum physics faster. That accelerated quantum research eventually produces better quantum hardware. Better quantum hardware, once mature enough, has the potential to make AI training and inference dramatically more capable. And more capable AI systems then get pointed right back at quantum research, closing the loop and speeding the whole cycle up again. That is not a metaphor, and it is not marketing language. It is an accurate description of what is actually happening inside these labs right now, even if the pace of that loop is still limited by very real engineering constraints that nobody has fully solved yet. Google's own research teams have started describing this pattern publicly, calling it a cycle running from fundamental research through to real products, and noting that AI is now accelerating that cycle in ways that let researchers tackle bigger questions with faster turnaround than was possible 2 years ago. Google has also expanded its hardware bets beyond its traditional superconducting approach, opening a research effort focused on neutral atom qubits, the same general category Atomic is pursuing, suggesting the industry sees enough promise there to hedge across multiple architectures at once. None of this means the loop is spinning out of control. Every one of these breakthroughs still depends on physical hardware that has to be built, cooled to temperatures colder than deep space, shielded from stray noise, and painstakingly debugged 1 qubit at a time. Artificial intelligence can propose better materials and architectures far faster than a human team working alone, but someone still has to fabricate the chip and confirm the results hold up under real conditions. That gap between a promising simulation and working hardware is exactly where Microsoft's claims are currently sitting. And it's exactly the gap Google's Willow result and the early oratomic experiments have already crossed. The distance between those two states is the entire story right now, measured in careful, unglamorous laboratory work rather than press releases. I think the honest, useful way to think about all of this is to hold two things at once. The underlying trend is real. Quantum computing is not 5 decades away anymore in the way it felt a decade ago, and artificial intelligence really is becoming an active tool inside the research process, rather than just a downstream beneficiary of it. The security implications around post-quantum encryption are not exaggerated, and if you work anywhere near data security, infrastructure, or long-term data retention, the shortened timelines coming out of the Caltech research deserve your attention regardless of how the Microsoft story eventually resolves. At the same time, not every claim wearing the label of quantum breakthrough deserves equal trust. Extraordinary claims from a single company, without independent replication, without peer review, and with a documented history of retracted results in this exact area, should be treated with patience rather than excitement, no matter how impressive the marketing materials look. Real breakthroughs get replicated by outside labs. They survive scrutiny from scientists who have every incentive to find the flaws. They do not depend on a single press release from the company that stands to benefit financially from the announcement. The Willow result cleared that bar. The Oratomic and Caltech paper is moving through that process now, with enough serious institutional reaction already that it is being taken seriously well beyond the company's own marketing. Majorana 2, as of right now, has not cleared that bar, and treating it as equivalent to the other two would be a mistake, however exciting the underlying story sounds. What you should actually take away from all of this is not a specific prediction about when quantum computers will break encryption or cure cancer, because anyone giving you a confident date on either of those things is guessing. What you should take away is that the boundary between artificial intelligence and quantum physics really has started to blur in a way that is producing measurable, documented consequences. From shifted corporate security deadlines to genuine peer-reviewed speed records to a $17 billion public market bet on a technology that still loses money on every contract it signs. The story is not as clean or as immediate as some of the more viral videos on this topic are making it sound, and it is also not nothing. Somewhere between the skepticism of the physicists rolling their eyes at Microsoft and the genuine alarm of the cybersecurity researchers watching the Caltech numbers, there is an accurate picture of where this technology actually stands in the middle of 2026. It is closer than it was 2 years ago. It is not as close as the headlines want you to believe. And the honest version of that story, it turns out, is still remarkable enough on its own without anyone needing to exaggerate it.